Alright, so now let's assume that you are given this equation. This is a rectifier, it's a full bridge. So we know that what is here is our AC in, and what comes out here is DC out. Okay, so you are asked to calculate the efficiency of this rectifier. So we know efficiency is PDC over PORMS. And then PDC is the same thing as IDC VDC. So it means that we need to calculate our VDC. So VDC, we said is 2 VM over pi. Okay, so we have 2 VM over pi. What is VM? The peak value of this 220 volt supply. Okay, V peak there. V peak is root 2 by V RMS input. This is RMS input, which is that 220. So I have root 2 times 220. So if you multiply that, you get 311.1 volts. So 311.1 volts. So we'll get that here. So VDC will be 2 by 311.1. Okay, divided by pi. So you have that as 198.05. 198.05. Okay. Now, remember that the VRMS here, this 220 input here is a VRMS, okay, input. And from what we derived before, the VRMS of this waveform is also V peak divided by root 3. So, divided by root 2. So it means that the input VRMS, okay, is the same thing as output VRMS. So that means the VO RMS is same as this source voltage, right? Which is 220 in that case, which is 220. Now, so we have VDC. We can also calculate IDC. Remember that IDC is a VDC over R, and we have resistance 5 ohms, and we have VDC as 198.05. So you divide by 5. So you get 39.61 amps. All right. So it means we have this, we have that. So that means we have this. So PORMS is the same thing as IORMS, VORMS. So you should know that VO or IORMS, let's say VORMS is the same as 220. So that is 220 volts. Remember what we said, that what we derived before is that VRMS is root 2, V peak over root 2 is VRMS, okay? So, and then, so root 2, by that will give you V peak, all right? VRMS here is the same thing as source voltage. All right, so it means we have VORMS, and then IORMS will also give you the same thing as VORMS all over R. So and VORMS is 220 divided by 5. So have 220 divide 5, get 44 amps. Okay, so we have that, we have that. So we can easily calculate the efficiency. So efficiency now is PDC which is IDC VDC, where we have our IDC 39.61 times VDC 198.05 divided by PORMS, where we have VORMS or IORMS 4 by 4 times 44 times 220. Okay, so we get something like that. So we have 39, so you get about 0.81. Okay, so you get 0.8104, which is 81.04%. Okay, so you can use this other way to solve it, or you use this way by using VD squared over R divided by VRMS squared over R. Okay, to give you VD squared over VRMS squared. So you get 81%. So the next is to calculate form factor VRMS divided by VDC, and we have our VRMS as 220. We have our VDC as 198. Okay, so you just divide that. So when you divide that, you will get 1.11. Then you can also calculate ripple factor. Ripple factor is form factor squared minus 1. Okay, so that you will get 0.4841. Then you can also calculate the transformer utilization factor, which is PDC over VS IS. So PDC, we know already, PDC, which is VDC IDC, okay, over VS IS. So we got the VDC calculated 198.05, IDC calculated 39.6. The VS is also 220, the same thing as that's the source voltage, and IS, okay, that we can calculate. So we use the same thing, the same method. Okay, so we'll have, remember that IS is the same thing as VORMS divided by the resistance. Okay, so you get 44. Okay, so now, so just substitute, you get 0.81. Now the peak inverse voltage. Remember, the peak inverse voltage is how much voltage at this, the peak that this diode can block, any of the diodes. So if this is going forward direction, like that, on reverse, this has a block, or even now, this one, this cannot go through here, so this has to block the peak value of that. So peak inverse voltage is V peak, which is 220 times root 2, because we know that VRMS is V peak over root 2. Okay, so V peak is 220 times root 2. Okay, so you get that as 311.1 volts. The crest factor is root 2, and then the power factor, which is our PAC over ISVS. This PAC over ISVS. PAC is VORMS, IORMS. So, and VORMS is 220. IORMS is also the same as 44. Even here, V source is 220, and the IS is 44. Okay, so this should give you 1. Okay, so let's have a look at the characteristics of the waveforms depending on the kind of load. You know that if this is resistive, all right, so the voltage will look just normal like that, as it is. So for resistive load, and you know that once you are able to get this voltage, let's say this is our voltage, and you divide this by resistance, okay, V over R will give you I. So I should be a little bit smaller. So I can take like that, okay. So this is our VO and that is our IO. But this will look like this only if this load here is resistive. But if it is highly inductive, let's see. If it is inductive, all right, you get for a highly inductive load, you get the current or IDC being equal to RMS. So the current will look almost flat. Okay, as you increase the inductance, as if I add an inductor here, as you increase the inductance, this ripple current will begin to disappear. All right, so it will start disappearing, reducing, like that. Okay, until when you have a highly inductive load, then you will see it very straight. Okay, and in that case, the IDC will be the same thing as RMS, unlike when it is resistive. Okay, so just note that for highly inductive system, IDC equals IRMS, and then the source current, you see how the source current will look like. This current here, remember that before you connect this, all right, the voltage is like that, and then the current will be like that also. But immediately you connect, if you connect this to, if you supply this, maybe you have a load, a normal resistive load here without the inverter or rectifier, okay, you get something like this. But immediately you put rectifier here, and this is feeding that. So this current is not going to look sinusoidal, pure sinusoidal like again. It's going to contain some harmonics. All right. So when you have something that looks like this, let's say harmonic, it means it contains a lot of harmonics. All right. So that is why we said a rectifier on its own injects harmonic back to the supply. Okay, it injects harmonics back to the supply. It actually acts as a nonlinear load. All right, and then the current through the diode will also look the same. Okay, like the source current. Now let's look at just this example. You have a bridge rectifier that has to supply 198 volts DC, 2,500 watts, highly inductive. Now, assuming ripple free, there is no ripple because it's highly inductive. In other words, IDC equals IRMS. You are asked to determine the supply voltage, the RMS of the load, the supply current, the RMS and DC current for one diode, and the apparent power of the transformer. Okay, so you are given this question. In this case, the source voltage you don't know, right? So you are only given something like this. You have the VDC and the power, and they say that this is highly inductive. For highly inductive, and you're asked to calculate the supply voltage, Vs. Supply voltage. All right, so since you are given this, you know already that VDC is 2 Vm over pi. All right, so and this Vm, root mean square, Vrms, this is input RMS, is V peak over root 2. So it means if I want to get V peak, it becomes 2 Vrms. So this Vrms we're talking about is this source voltage. Okay? So in other words, this can be written as 2 by root 2 V source, okay, divided by pi equal to VDC. So the same must calculate the source voltage. Okay, I just need to calculate that Vrms. Right, so which you can make subject formula. So VDC by pi over 2 root 2. So VDC is given to you as 198 times pi by root 2 times 2. Okay, so you get, that's how you get 219.9. So next question, we are asked to calculate the IRMS for the load. Okay, IRMS for the load. So what do? Now, we need to calculate, since this is purely inductive and it's ripple free, it means that IRMS here equals IDC. So IDC equals IRMS. So IDC here equals IRMS. So this is almost like a straight line. Okay, so the IDC in that case becomes IRMS. So, but what is IDC is VDC over R equals IRMS. We are asked to calculate, I just want to get that again. We are asked to calculate IRMS, okay? Calculate IRMS. So we know this, but we don't know this. But to know, we can use this power and this voltage to get the resistance, okay? So if we want to get the resistance, I have V squared over R is that P, okay? So we can easily calculate that. So the P is given to us as 25. That means R is V squared over P, which is 2500, which is 198 squared over 2500. Now, just to get R, we put it here, and then we'll get a value. All right, so so 2500 over 198 will give you 12.63. So remember, we can use any method as far as you know your Ohm's law. Okay, like what I'm doing here now is 198 squared divide 2500. Okay, so you get 15.68. That's the resistance, so we put it here. That means that RMS is VDC. Now VDC is 198 all over resistance, which is 15.68. 0.68. 198 divided by, that will give you 12.63 amps. Okay, if you check here, just the same thing as 12.63 amps. All right, so the next question is to calculate. So anyhow you want to use it, okay, as far as you know your Ohm's law very well, okay, then you'll be able to get the same answer. Now the next question is to calculate the supply current, and we know that for a ripple free, okay, IS is IRMS, so which we have calculated to be 12.63, and then the current through the diode, we said from our previous class, that's a DC current divided by 2, so which is 12.63 divided by 2, that gives you 6.315. And then ID, RMS is IRMS over root 2, and our IRMS is 12.63 divided by root 2, you get 8.93. Then you are also asked to calculate the apparent power of the transformer, which is IS VS, and VS is 219.9, IS is 16.3, so you get 2777.34 VA. Got it?